You have encountered mass density and concentration already in high school. These are also very important in continuum mechanics. So, what's the problem? Well, as long as you do not think too much, there is no problem. However, once you start thinking a bit more deeply, you will notice that there actually is a problem. And that is exactly what we are going to do. But do not worry, we do not only discover a problem in this video, we will also solve it. So, what again was mass density? Well, you take some object, you compute its mass, you compute its volume, and the mass density equals delta m over delta v, the mass divided by the volume in kilograms per cubic meter. Well, often this density is not constant, so what you then have to do, take smaller and smaller objects and take the limit delta v to 0, so the local density in every point, rho is a function of space and time, it's then limit delta v to 0, delta m over delta v, giving dm dv. So, no problem so far, but then something fishy is happening. Can we take this limit delta v to 0? If we make our volume smaller and smaller and smaller, eventually we will run into single molecules or single atoms and ions. So, can we take this limit? Well, now there is a very important assumption in continuum mechanics that we basically neglect this very small structure. We just pretend they are not there. So for our model, we think we can take this limit as if there were no molecules at all. And then eventually we will compute integrated quantities, so it's no problem for our big objects, but some subtlety is going on. We ignore the structure of the molecules and so on. And then we are fine again, because what do? We have our rho equals dm dv, so we have a dm equals rho dv. So our total mass will always be some integral over our region, a big region R, rho dv. And similarly, we can use the same trick for the concentration. Concentration locally is the number of moles or number of molecules divided by the volume, and then take dv to 0. Again, this same trick, because actually if you really take the limit, you will run into single molecules. It's either a molecule or not. But we ignore that again. So we just take the limits as if the single molecules were not there, as if we have a continuum. And then in the end, we compute large quantities, like the total number of molecules in a big space R, by integrating our local concentration over the volume. Now we have a small example of that. Say we want to compute a mass of a sphere with non-constant density. I just took some density rho equals r over capital R rho 0. So the small r is the distance from the origin till the point where you are, and capital R is the radius of our sphere, and rho 0 is the density at the boundary, where r is, as usual, x squared plus y squared plus z squared. So how can we now compute our total mass? Well, we have our formula. We just have to integrate over the entire sphere. So m equals triple integral rho dv. Now you see we are symmetrical in the angles in theta and in phi. So we have the integral 0 to 2 pi over d theta, 0 over pi d phi. It should be a rho of times. And then the integral 0 to r of our density rho, and this is the Jacobian. So what do we get? Well, the integral over theta will give us 2 pi. The integral 0 to pi over sine phi will give us a factor of 2, so that's the 4 pi. In the density we have our constant rho 0 over r, which goes here. So we are left with one factor of r and an r squared from the Jacobian to give an r cubed. We integrate that, we get r to the power 4 over 4 between the boundaries. And we can simplify a bit, cancel out the factors of r here, and cancel out factors of 4 to get pi times rho 0 times r cubed. So there we have the mass of our sphere. Well, the essence of the example is that once you have your densities, once you have your local density, you can compute masses by integrating over the region.